Hello, uh, welcome you all for unit number 3, mass transfer operations. Here in this class, we'll be looking into the extraction second part. As I discussed in the previous video, uh, we will be looking into the second part of the extraction series, that is multi-stage operations, countercurrent and cross-current operations we'll be looking into, and a numerical based on that. So before that, we'll look into what is uh, countercurrent operation, what is cross current operation, how are they different. Different options will look into this, and importantly these are multi-stage operations. That means more than one stage is associated, so this extraction operation repeats the time. So you have a feed, obviously you have a feed, you have a solvent, the products raffinate and extract. Obviously these are the four components that are involved in each stage, but how they are arranged, based on that you have the different staged operations. Now coming to the first one, countercurrent operation. Countercurrent, as you know, opposite direction. The feed is entering the stage 1, leaves as raffinate 1, and that raffinate 1 enters the stage 2 as the feed. Then it leaves the stage 2 as a raffinate 2. Raffinate 2 becomes the feed for the stage 3. Stage 3, the product is raffinate 3, and likewise it may go on to the next stages 4, 5, like that it go on. Whereas the solvent enters in the opposite direction and it enters the stage from the end, that is the last stage it enters. Fresh solvent is entering there and it leaves as the extract from that particular stage. Since it is stage 3, it is named as extract 3, and that becomes the solvent phase, and that enters stage 2, and it forms the extract phase and it leaves the stage 2. Since stage 2 is numbered as 2 here, so that's why the extract phase also numbered 2, and that forms the solvent to the stage 1, and it exits as the extract 1 from the stage 1. So if you look at the flow arrangement, feed once enters and it just continues through all the stages. Solvent, once it enters from the last stage, it passes through all the stage and it exits the first stage. So this is the countercurrent operation. Now if you look into the another one, that is cross current operation. So here the feed enters, exits as a raffinate 1, which will be the feed for the stage 2. Then that raffinate enters the stage 3 and it exits. The solvent doesn't enter the last stage like this. Unlike that, the solvent enters the stage 1 and it leaves as extract. So this extract is different and it never reaches the stage 2. So it doesn't go to the stage 2. For the stage 2, a fresh solvent is added and that from the extract. Fresh solvent is added to the stage 3, that becomes the extract 3. So when you compare it, you have only one extract as the final product. Here you have number of extract equal to number of stages you have. It can go further, but if you have n number of stages, you have n number of extracts coming out. But the feed is 1, it just continues through the stages and there will be only one raffinate. Here there will be one feed and there will be one raffinate at the end of the whole process. Now this is cross current operation, this is counter current operation, and one more, you have parallel current. It looks similar to the counter current, but the difference is feed and solvent are entering from the same stage, not in the opposite direction. They are moving in the same direction. It is almost similar to the counter correction in the concept of entries and exits, but in this directionality is uniform, same side. So the difference, what it matters here is the efficiency of the overall process, how much you can recover, how much solvent is required in each type of the staged operation. That's what matters. So in order to identify how that matters, how you calculate theoretically, we can have calculation, that is number of stages, how much required, how much quantity of the solvents required, you can measure it, provided you have equilibrium data. Now let us see how we can do that. Let us take one case. Let us take the cross current operation, which is quite commonly used. Uh, Now let us look into this particular case. I have taken only two stages. So the feed enters uh, cross current means you have solvent entering and leaving as extract, solvent entering and leaving it as extract, E1 and E2, and the feed enters the stage 2 and leaves it as raffinate from the stage 2. So I have given some notations here for our analysis purpose. So F0 enters the first stage and exit is F1. To F2 means exit of E2, second stage. E2 stands for exit of 2, E1 stands for exit of 1. So that number 1 refers to the stage number. So throughout I have maintained the same way. Now usually this is used as a batch extractor, and for low capacity usually we use it for washing and neutralization purpose, where the concentration of some solute in the feed should be reduced. Our interest is not this product, or this product what we get extract. This is not our interest. Our interest is to remove that impurities from this particular feed solution, so that X2 is very low. That's our main target. So in such situations we usually use cross current operations, because the solvent quantity required will be very high in this case. uh, okay, let's do the material balance stage 1. Let us do the analysis by stage. Let us take only one stage for the time being. Let us not do the overall balance. Let us do the steady state solute balance. Only solute, let us take it, the quantity total multiply the concentration in each. So the X stands for the feed solvent phase, that Y stands for extracting solvent phase. Now if you look at the equation here, F0 into XF inputs, S1 into Y0, the concentration is Y0 here, S1 into Y0 is equal to E1 into Y1 plus uh, F1 plus X1, this one. Now if you say that the solvents are totally immiscible, that means this feed solvent does not enter the extract phase. In that case, this F's all will be equal, this S will be equal to E. Otherwise F is equal to R. Let me say that F0, F1, F all are equal, F0, F1, F2, F3, like that it goes on, all are equal. And S1, E1, this S1 and E1's, S2 and E2 all are equal. So let us have a common terminology for this. F0, F1, F2 all are equal to F. So let me retain it as F only throughout. Whereas S1 and S2 or E1 and E2, since all of them are equal, let me retain a common notation S. So considering this, just if you replace this particular equation with this particular concept, wherever you find F0 and F1 you put F, S1 and E1 you put it as S. So rewriting this, F into XF, S into Y0, S into Y1, F into X1. We will rearrange the equation. How do we rearrange the equation? Let important item information that you need to remember is this X1 and Y1 products, they are in equilibrium with each other. So this Y's let us combine, this X's let us combine, that is Y and Y let us combine, this X and X let us combine. Now when I'm combining, I'm seeing that is Y1 and Y0 are taken on side, that is Y1 minus Y0, both are having the common term S, and this side XF minus X1. Instead of XF minus X1, let me keep it as X1 minus XF. It's supposed to be XF minus X1, but I have taken the minus sign here, so I can write it as X1 minus XF. The common term is F between the X, common term between the Y's is S. So it forms, if you rearrange this equation, you will get an equation like this. This is called as operating line. And if you observe here, I have taken Y1 as the first term among the delta, X1 as the first term among the delta. And you should remember Y1 and X1 are in equilibrium with each other. That is the reason behind taking this minus and reverting this signs. Okay, let's analyze about that operating line. That equation I have rewritten here. For a fresh solvent, let me say that this fresh solvent is 0. Y1 and X1 are in equilibrium. So this is the equilibrium line that you can draw. This is the equilibrium line, Y versus X. So some data is available, we have drawn the diagram. But this equation operating line is a straight line. You can see that Y1 and X1, they are the equilibrium data. They are having the power 1. So it's a straight line having a slope minus F by S. It's a negative slope. So it's a minus F by S. It is also called as feed to solvent ratio. Feed to solvent ratio. In case if you are asked to find out feed to solvent ratio, this F by S is the one which you have to calculate. Now if you look at this particular equation should pass through xf comma y naught, xf comma y naught. If y naught is 0, that is 0, xf comma 0, xf is nothing but the feed concentration, usually known to us initial concentration of the solute in the feed. So that particular quantity at 0, so that is this y value is 0 here, this horizontal line, and this xf here. From this point you have to draw one line such a way that the slope is minus f by s. It's written f by s, it's a negative slope, so it's a negative f by s slope here, this line. So once it is connecting over here, that is intersecting the operating line intersect the equilibrium line at this particular point, and the concentration of solute in two different phases, that is x and y, and this is x1t and y1t. These two values x1 and y1, these two values are here and here. Observe this carefully. The x is nothing but in the raffinate phase, y is nothing but the extract phase. So it has to be always extract phase in the y-axis, raffinate phase in the x-axis. Identify which is extract phase, which is raffinate phase before you draw. Stage 2, that is for the stage 1. Now let us move on to the stage 2. As I have told you, f1 and f2 all are equal to f, s2 and e2 both are equal to s. So considering that, so it is f into x1 is the input here, output is f into x2, output is f into x2. Input here is y0 into s, output is s into y2. That's what I have. Two inputs, two outputs. Rearrange the equation as I told you earlier, same logic holds good. Note that y2 and x2 are in equilibrium, y2 and x2 are in equilibrium. So the input concentration is x1, input concentration is y0 for the solvent. Again the same logic, if y0 is 0, it passes through x1 comma 0, it passes through x1 comma 0, which with the same slope minus f by s. The slope f by s does not change in both the stages. So from here you draw one more line, and when it intersects the equilibrium line, that is going to be the concentration of exit concentration of stage 2, equilibrium concentration of stage 2, x2 and y2, this x2 and y2. So generalizing, for any ith stage you can write it as yi minus y0 is equal to minus f by s, xi minus xi minus 1. So it's the most general form of operating line for the cross current operations. Remember, we have dealt with only the immiscible solvents. In case if there are partially miscible solvents, case will be slightly different. Let us go to the counter current operation with immiscible solvents. We have seen this earlier also. So the feed enters on one side, solvent enters on the other side. That's what I have written here. Fresh feed with the solute is fed to the first unit and leaves the raffinate as R1. This stream passes through the units and leaves from the nth unit, last unit, as Rn. Whereas the fresh solvent, yes, it enters the nth unit, freshly enters there, and leaves the extractor unit, this particular nth unit, it leaves as En. Then it passes through all the stages, and at the end it will be having E1. If you do the material balance for first stage and nth stage, randomly we'll take two stages, first stage and nth stage. First stage, if you take it, remember the same logic holds good, f s f s. What I told you earlier, that is all feeds and raffinate streams are equal in quantity, and e's and s's, all what you have, all are equal in quantity. So for this particular case, f into xf plus this s into e2 input will be equal to f into x1, r1 is f, s into y1, this e1 is s into y1. Similarly for the nth stage, if you do it, you will get this particular notation, f into xn minus inputs, here it is f into xn minus 1 plus s into yn plus 1, f into outputs, f into xn plus s into yn. Now let us take whole unit, all the units put together. If you look at the material balance, everything together, the red box what you see here, the entries are like this: feed enters with the composition xf, solvent enters with the composition yn plus 1, raffinate exits f quantity with the xn concentration, solvent yes exits with the composition y1. So if you take this particular case here, what do you get? F into xf, f into xf plus s into yn plus 1 is equal to f into xn. Where is fx? Yeah, this one. F into x1 plus s into y1. This is y1. S into y1. S into y1. This is y1, not one just y. It's y1. Supposed to be 1 here. So rearranging the equation, the most important thing here is, as I told you earlier, simplifying the terms. That is, you can take this side also, as we have done earlier. Y1 you can take it to this side. Yn plus 1 minus y1 is equal to f by s, xn minus xf. Xn and this where is this xn and yn, these two are in equilibrium with each other, so that xn and yn doesn't come into picture here, yn doesn't come into picture here. So that's the most important critical thing that you need to know. So this is one straight line equation. If you see it, all x and y are of the power 1 only. So let us analyze how we solve it using the equilibrium diagram. So operating line and equilibrium diagram both are drawn. So this is the equilibrium line, the upper one, curved one. This is the operating line. How did we draw this? The most important item you need to observe is this solvent is fresh. This solvent is fresh, so it is yn plus 1. What we get here, yn plus 1. This will be 0. So this will be 0. This term will be 0. Given other information, you can find out the remaining terms and you will be able to draw the operating line. Now, how we draw the operating line? We'll solve a problem and then say it. Now, given the composition xf from the operating line, you can move on to the equilibrium line. That is, this is the starting point, this is the operating point, and once you mix it and leave it, it reaches an equilibrium. The composition of equilibrium, this is the equilibrium point, this is the output of the stage 1. The composition is y1, composition is x1. Now it doesn't end there, this enters the new stage, stage number 2. So the entire thing happens within stage 1. This triangle refers to stage 1. So here the stage 2 starts. So it operates, stage 2 starts, it mixes with the solvent, it reaches an equilibrium. At the end of equilibrium, it forms a concentration y2 in equilibrium with the x2. So this is the stage 2. So this entire thing is stage 2. Likewise, further stage goes on up to the last xn. So this is the end of the operating line. So the number of stages here you have is this side 1, 2, 3, 4. So there are 4 stages involved. That way you can calculate the number of stages. So this particular equation always, it also passes through xf and y1, xf and y1, then xn and yn plus 1, any random value xn, this xn and yn plus 1, these things can be calculated. So let us see how that value refers to. In fact, yn plus 1 and xn are the available values, and we'll see how that works out. Yeah, this is the stage 4 sections it is divided. Okay, here is the problem. This problem is common for one of the common problem, simple problem that you can get, that is single stage operation. Read it, pause for a second and read it. Alright, let us see how do we solve the problem. You are given with the x versus y data, an important issue. Second one, the feed constant quantity 1000 kg per hour, that is the feed, total feed is given to you, but the quantity of the solute in that is 1%, that is 1% nicotine, which is very low. Even, and the product concentration is 0.1% raffinate concentration. So in the liquid it reduces from 1 to 0.1%. that you can say it has very low percent margin of error. So considering that, you can say 1000 kg is equivalent to pure water only without nicotine. That forms the solute free basis. So we are going to use that particular concept. Now you can write a block diagram, same FXF SYS EIE. Here it is not mentioned whether it's a multi-stage or a single stage. So normally solvent requirement, minimum solvent requirement, we generally go for a single stage operation here. So the input and the output are given to you. Let us assume that it is completely immiscible and the solvent is pure. So YS is equal to 0. Write the material balance equation for the solute. Then substitute. Once you substitute the values, available values, when you substitute into this equation, you see that there are two unknowns. One is S, another is YE. So you have one equation and two unknowns. You can't solve it. You have to know, you should be knowing any one of this. The requirement is yes. Question is on yes. So let us try to see whether we can solve this YE. We have been given with the composition X versus Y data, which we can plot. X versus Y, you can plot the data. If you see it, I have taken only three values, 1, 2, 3 of the whole data set. I have not drawn all the whole graph. I have taken only three because my requirement, that is you have to calculate YE, and this YE I know that it is in equilibrium with XR. So this XR and YE, they are in equilibrium with each other. This XR is given to me, that is 0.1%, that is 0.001 in decimal scale. So that data is known to me 0.001, which is less than this. So that's why I have taken 1, 2, 3. Three data I have taken, only three data I have taken. If at all I plot it, there will be a big graph and this particular information will be hidden, and manually when you draw the graph it will be difficult to identify these values. So my suggestion is select only those number of data points as much required. Don't draw the graph for all possible values. So at XR is equal to 0.001, here at 0.001, find out from the equilibrium curve what is the value of Y. That should be this YE. So that is 0.0008. Now if you substitute here and calculate the value of S, it is 11,250 kg per hour. That much solvent is required if you go for single stage operation. Let us solve the same problem, but here the question is slightly different. Instead of 11,250 kg per hour solvent, let us take 1,500 kg per hour of solvent, and let us use cross current extraction, multi-stage operation, not one single stage operation. We'll go for cross current extraction. Just observe the diagram, just recall what we have seen earlier: material balance and operating line. Now the quantity that are given, we have written it 1000 kg per hour, 1% nicotine, and 0.1% nicotine is the final concentration. Remember, it's the final concentration, not for the stage 1, final at the end of the stage. This is not two stage operation, it is multi-stage. Instead of, I don't know the number of stages, so that is why I've taken only two as a representative case. There can be many stages, so I've taken cross current operation. For each stage 1500 kg per hour of solvent is fed. So the operating line for the cross current case is this: any number of yi minus y naught is equal to minus f by s xi minus xf. So any information that I know from this block diagram I substitute. Y naught is 0, yi is in equilibrium with the xi at any stage. The two compositions, sorry, this one xi and yi and xi, these two are in equilibrium with each other, which I don't know. Xf, initial concentration is 0.01, 1% is 0.01. F by S, 1000 by 1500. So this is the equation. So the slope of the operating line is minus 2 by 3, 1000 by 1500 is 2 by 3, and it passes through xf minus comma y naught, xf 0.01 comma y naught 0. So I need one more data, that is instead of getting 1 point and a slope to draw the line, it's better to always to have 2 points. So one is this, the line passes through this. I'll take one more point, y at x is equal to 0.004. At this particular value I'll take it at 0.004, and when I substitute into this equation I'll be using, what I've done is I've taken this xi, this xi I have taken it as 0.004. If I take this value, what is the value of y? That will be again 0.004. So this operating line passes through 0.01, 0 and 0.004, 0.004. These 2 points you draw it, connect them. It's a straight line with a slope minus 2 by 3. Let us see that. This is how it is. Look at this. This is the equilibrium curve. This blue line, equilibrium curve, and operating line. It passes through these 2 points. Here, one point is here, another point is here. I have connected it using a straight line, but I have taken it up to equilibrium line. This is stage number 1. So at the stage number 1, composition is this, and this is the another composition. This is the exit concentration of stage 1. So here the stage 1 ends. This will be the feed composition of stage 2. It enters the stage 2. Remember, slope remains the same, f by s. You have to draw one line parallel to this. You draw one line parallel to this and connect it. This particular line is parallel to this. It connects over here, equilibrium. So this is equilibrium composition y and x. This is the stage number 2. Then again you have to draw one more parallel line. You have to go on drawing the parallel line. So when it reaches the equilibrium curve, that will be your exit concentration, that is the raffinate concentration here, and extract concentration over here. So this is the end point. How do I know that this red dot is end point? That value is exactly xr is equal to 0.001, that is 0.1%. Raffinate final concentration required is 0.1%, or xr is equal to 0.001. So this point. So I started from here xf, I have ended with xr. In between that, how many number of such curvatures I can draw, lines I can draw, equilibrium operating lines I can draw, that matters. So I have drawn one operating line, second operating line, third operating line. So totally 3 operating lines I have drawn. So there are 3 number of stages. So the number of stages is 3. In each stage we are feeding 1500 kg per hour of solvent. So the solvent requirement is 4500 kg per hour. Remember, recall the single stage operation where we required 11250 kg per hour to achieve the same thing. Alright, let us solve the same problem, that is with the 1500 kg of solvent only. Instead of cross current, let us go for counter current operation. In counter current operation, let us write the material balance. That is operating line will write it yn plus 1 minus yn is equal to f by s plus xn minus xf. Now this is the data that we are having given in the problem: 1% nicotine, 1000 kg per hour, solvent concentration, quantity and concentration, product concentration. These are known to us. This is the operating line that we have already derived. Substitute it. Yn plus 1 is 0, y1 is unknown, then f by s, feed to solvent ratio, xn is somewhere here, xn 0.001, xf 0.01, so y1 is 0.006. So the values are known to us. That is, the operating line has a slope 2 by 3. It passes through this value, which 0.001 comma 0, that is xn and yn plus 1, and another value 0.01 comma 0.006. So 2 points it passes through. It's easy to draw. You just have to take 2 values into this equation. You just have to take 2 values. You can find out 2 points. That is, you take x is equal to 0.001 and 0.01 at one time. So you get 0 and 0.006. 2 points you get it. Join the 2 points, you get a straight line. So this straight line is going to be operating line. So the data available to us: equilibrium data, operating line data. So you have to draw 2 lines. The blue line refers to the equilibrium line. The orange line here refers to the equilibrium line. How did I draw it? I have 2 points through which it passes: 0.001 comma 0. I guess this is the point, 0.001 comma 0. There is one more point. Draw this: 0.01 comma 0.006, 0.001 0.01 comma 0.006. This point. These 2 points you join it. The orange line is the equilibrium line, sorry, operating line. Then start from the xf value, end at xr, that is raffinate concentration is 0.001, feed concentration is 0.01. So start from here, move up to the operating line, then move to the equilibrium line, then again move on. So this is the equilibrium composition 0.006, and the value corresponding over here, that will be the equilibrium concentration of the stage 1, exit concentration of the stage 1, raffinate concentration, extract concentration. So this will be the feed composition. So the operating line, once it touches operating line, the stage 2 starts. This is the end of the stage 2 equilibrium composition of extract raffinate over here. So here the third stage starts. Likewise it goes on till you cross the XR value, usually number of stages are integer, that is if you take it 1 2 3 4, but here it is half done, it's not complete. That means it doesn't reach the equilibrium. So even if you do the fifth stage, if you complete the fifth stage, the composition will be lower than the XR. So we say that you don't have to reach the equilibrium, so the number of stages half for the reason is that it is 50%. You take a inverse lever rule, that is the total distance divided by this distance, that is 50% approximately here. So the number of stages is 0.5. So total number of stages is 4.5. Okay, analyzing it. So number of stages required in the counter current operation for the same case as we have done earlier is 4.5 stages. If you look at the solvent quantity required for a single stage, it was 11,250 kg per hour. For cross current operation, it was around 4,500 kg per hour. Now here it is 1,000 kg per hour, 1,500 kg per hour, because we are feeding only at once in the beginning to achieve the same concentration or the percent recovery. But the number of stages here is 4.5. Number of stages in the previous case it was 3. So the equipment increases, solvent quantity decreases. That's what you have to observe. So that's the end of the three types of the problem, that is single stage, two multi-stages. So some trick I can tell you over here when you solve the problem. One, do not plot XY plot first. Simply given the data, don't draw it. Draw to the required scale and use only the required values from the data set. If you remember, I have used only 3 data earlier. Here also, how many data I have taken? 1 2 3 4 5. 1 2 3 4 5. That means I have not drawn this data. That is, I have drawn up to 0.009, somewhere here, this value 0.00998, this value up to here I have drawn. The last value I have not taken. The reason is this is going beyond XF, so any value beyond XF is not required. So only the required information you draw it from the equilibrium curve. That's what I meant by this. Operating line. Now the two operating lines I have written. So from the what we have derived earlier, let us do the analysis. This is the equilibrium composition, yi versus xi, yn plus 1 is xn. In fact, this is not equilibrium value, but they lead to something. The line passes through these 2 points, xi comma yi, xn comma yn plus 1. There is another point through this the line passes. So if you have to draw the line, so xi yi is one point, y naught xf is another point. Why not? Here is this, yeah, y naught and xf. Here yn plus 1 and xn is one point, yn and xf is another point. So you should be able to find this set of data. This xi yi and xf y naught gives you the operating line for cross current operations, and here this particular point and the second point here xf y1, this gives the operating line slope for operating line data for counter current operation. And note that this is negative in slope and this is positive in slope. So xi y values here, xi and yi values, they are on the equilibrium line, so you cannot guess the value. It's very difficult to guess the value. So what you should do is you have to randomly select one xi value less than xf and substitute and find out yi, whereas here you can easily solve the problem. Yes, that's it. That's the end of the problem. Thank you.